So let me just see here. There we go. Um, Yesterday we started talking about freeze patterns and their associated symmetry groups. So let me just remind you of the definition that we gave yesterday. Okay. With the following. All right, I should say definition. A group of isometries that fix a given line C and whose translations form an infinite cyclic group is a freeze group. With center C. Right? And we left off yesterday noting that this is kind of annoying because, again, we're overloading the term center here. When we talk about the center of a freeze group, we're talking about a line, which is counter to how we've used center every other time in the course so far, right? The center of a half term is just a point. A center of symmetry is a point, right? But in this context, for a freeze group, the center is a line. Okay, and the other thing that was important to note is implicit in this assumption that I have an infinite cyclic group means that there's a single generator. I can write the subgroup of translations as generated by a single translation. Okay, that would be from this claim of the translations being cyclic. Okay, so here's the upshot. Here's what we can say about this class of group of isometry. There are exactly 7 types of freeze groups. Okay, so what we're going to do now is just puzzle out what those different groups are. Okay, and basically it's just a process of elimination, or just making some assumption about what it must contain and deducing the generators from that. Okay, so now what we'll do is we'll determine all 7 distinct freeze groups. Okay, so just a piece of notation here. All 7 freeze groups will say, we'll denote a freeze group by this script F with center C. And subgroup of translations the infinite cyclic group generated by tau, some translation. Okay. So I want to set up some more notational conventions so that we can make this exploration more concise. Okay. So let's see here. We're going to choose a point A on our center C according to 3 different cases. Okay, so depending on what our assumptions are, we're going to pick some point A on our center C as follows. So the first case, case 1, is if our Fries group F contains half turns, then we choose A to be the center of one of those half turns. Case number 2, if we assume that F contains no half turns, but does in fact contain reflections in a line perpendicular to C. Sorry, I should give that line a name, right? A line, let's say A, a line little a, perpendicular to C. Then we'll choose our point A to be the intersection of A and C. Not capital A, but little a and C. Okay. And otherwise, case 3, what do? We just take A to be any point on the line, C. Let A be any point on line C. So having these conventions, let us put down some more useful notation in the classification that we're going to carry out. So let's let a sub I be equal to tau to the ith power evaluated at A. Right? We're just applying our translation, which we know we have by the definition of a Fries group, to A I times. And of course, when to make this notation consistent, we allow A sub 0 to be tau to the 0 of A. Remember, usual rules of exponents apply for any group, right? So tau to the 0 is just the identity, right? That is to say, A sub 0 is just A. Okay, so also note that tau to the n of A sub I is equal to tau to the n plus I of A. So that is to say, what this means is that every translation in my Fries group F must take AI to AJ for J. Okay. That is to say, once I've made this choice of a point on the line C, all my translations in F just permute those points. You just move each of them around, depending on what the translation is. Okay. Okay. So I know this might seem as though we're just putting a lot of notation down, but this is going to be extremely useful to us, I promise. So just hold on a couple more minutes. Okay, so let's also let M be the midpoint of A and A1. Okay, so furthermore, you might well guess that MI is defined similarly to A sub I. It's just applying tau I times to M. Okay, which of course implies that MI is the midpoint of AI and AI plus 1. But there's more. and also mi is the midpoint of A0, i.e. A, and A sub 2i plus 1. Okay. So that is to say, if I'm the midpoint of AI and AI plus 1, well, in fact, I can go all the way back to A and then find something that's equidistant from A to MI that is a translation of A. Okay, that will come in handy to us. Okay, so with that, we're ready to start making our classification. Okay, so possible Fries groups. First possibility. Let's set F1 just equal to the group generated by just tau. Okay. Remember in the definition, there is the definition of Fries group. There's no requirement that we contain anything beside translations. So this is the simplest possibility to start with. Okay. So for each of these possible Fries groups, I'm going to draw you an example of a pattern that has that group of symmetries. Okay, and we'll incorporate all the notation that we set up just now beforehand. Okay, so let's just say a pattern having this symmetry group first of all has no point of symmetry, right? That is because there's no half turn contained in just the group generated by a single translation. No line of symmetry. Again, because there's no reflections in this group generated by tau. And furthermore, n is not fixed by a lag reflection. Okay, so here's a pattern. Let me just put this for you. Okay, so what do we have here? We have A0, M0, A1, M1, A2, M2, A3. So I'm using solid dots for A's and hollow dots for M's. So here's an example of this pattern. Well, let me just add another. Okay. So I'm just choosing something very simple to draw that's chiral, right? That you can't flip, right? So this is an example of a pattern having this Fries group F1. So now what we're going to do is systematically add rotations, reflections. When I say rotations, it'll turn out that we're restricting ourselves to half turns, but we're going to add in more types of possibilities for isometries that can be contained in our Friese groups. Okay, so obviously this one is not that complicated to puzzle out, but the others will take a little bit more work.
Professor, I find it's kind of like harder to write the stuff on the bottom because just like while you're presenting, your body's kind of blocking. It's also the least often showed.
Okay, so should I avoid writing on the bottom, or I'll just try to be more conscious to step out of the way?
I'm just saying whatever method works.
Okay, but you are able to read what's at the bottom of the board, right? It's just me being in the way.
Yeah, just
okay.
that the time it's open is like the shortest amount of time.
Yeah, okay. I'm gonna try to do much better at that. Thank you. Okay. So before we move on to case 2, let's make some observations. So first of all, other than translations, the only even isometries that fix the center which I'll remind you again is a line here. Are the half turns with centers on C. Okay. So then let's suppose. So suppose F, some arbitrary Friese group, contains a half turn say sigma sub A. Using our chosen point A as center. Right, we have this complicated methodology for finding A. So since we know A is a point on C, we assume that F contains the half turn centered at A. Okay. So also note also that the half turn centered at M is equal to the half turn centered at A followed by translation. Right? Remember, M is the midpoint between A and A1. Okay. So by our theorem from yesterday, remember, our theorem from yesterday said that if, let me just quote that for you. If P is a point of symmetry for a set S and alpha is a symmetry of S, then alpha of P must also be a point of symmetry for that same set S, right? Okay. So, so by that theorem, what we have is that sigma sub AI and sigma sub MI are also in F. Let's just quickly compute that, right? So again, we have sigma M equal to tau sigma A, which implies that sigma M tau inverse is equal to tau sigma A tau inverse, right? And what do we know we can do when we conjugate a half turn by some isometry? How do we deal with that? Well, we just take the isometry that we're conjugating by and operate it on the center of the half turn, right? So this is equal to sigma sub tau of A, right? Which, of course, is just sigma sub A1, right? So what I'm saying is, remember, what is a point of symmetry? Well, a point of symmetry is the center of a half turn that is a symmetry of some set, right? So now we're saying that this must be in F, right? So that is to say, A1 is also a point of symmetry of some pattern that has this as its group of symmetries, okay? So then we use induction, right? That is to say, I can repeat the same argument by conjugating sigma A1 by tau. Okay, so here's our homework exercise. Show that sigma mi must be in F. Okay, very similar argument, but you know, good to practice. Okay. So, with all that in mind, all of that in mind, okay, let's suppose that P is the center of some half turn in F. Okay, so suppose P is the center of some half turn in F. Then we must have the following. Then the translation sigma P, sigma A must also be in F, right? And remember, this goes back to one of the first things we proved about translations is that you can express them as a product of half turns, right? And vice versa. If you multiply any two half turns together, you get a translation. Okay? So we know by the definition of Friese group that the translations are an infinite cyclic group, meaning that sigma P, sigma A of A is equal to AN for some N, right? This is just by the notation that we constructed before, right? Okay. So let's unpack this in a different way. If we were to compute this directly, what would we get? We get sigma P, sigma A of A. Sigma A of A is just A, right? Because A is the center of this half turn. It's fixed by that half turn. So we get sigma P of A is equal to A N. Now, what does that tell us about P? Sorry, this is a capital P, of course. I made that look kind of lowercase. What does this final equation imply about P? So it is on the line C, good, but it also tells us that P is the midpoint of A and AN. Right? If I take point A and rotate it 180 degrees about point P, that means P is the midpoint between this input point and the image. Okay? So this allows us to make a fairly strong conclusion. Therefore, the half turns in F, some Friese group, are centered at AI or MI. Okay. So let's just take a step back here and think about what we're doing. I described a way that you can choose a point A on the center of a Friese group. Okay? And now what we're doing is using that chosen point and all its translates, its image under tau iterated to determine the possibilities of what F can contain, what the structure of F is. Okay. All right. So now we can move on to possibility 2 for a freeze group. Okay, so let's set F2 to be equal to the group generated by tau and the half turn centered at A. Okay, so not surprisingly, this is how this is going to work. We're just going to successively add in more elements and see what we get, what the possible outcomes for the total group are. Okay, so let's talk about the structure of this a little bit. Then we have, remember, we said this in our preamble, that tau sigma sub A is equal to sigma sub M. So obviously, since this is a half turn, this product is also an involution, right? Is an involution. So what does that tell us? It gives us the somewhat useful equation that tau sigma A is equal to sigma A tau inverse, right? That is to say, if I invert this product, I just take the reverse order and take the inverse of each factor, right? Okay. So this in turn implies every element of F2 is of the form tau to the I or sigma A tau to the I. So right. So additionally, we can write this as a different set of generators, right? Remember, the generators of a group are not unique. Okay, so this is worth saying because I can write this F2 in a form where it appears as though I'm omitting the translation, but bear with me. So, of course, since sigma n tau is equal to sigma A, we have F2 is equal to the group generated by sigma A, comma, sigma M. Okay, so that is to say, when I write it in this form, it's not transparent exactly where tau is. But of course, remember, the product turns is a translation. So that is to say, sigma m times sigma a is just equal to tau. So that's where the translation appears. Okay, so both of these are equally valid, but if you see a group generated by two half turns that lie on the same line, and one of which is the midpoint of, yeah, right. If A and M have this relationship, right, that we set up in our notation in the beginning, then that is in fact a Friese group, even though it's not explicitly generated by some translation. Okay. The point is that when you consider a group, regardless of the generators that you're given, to verify it's a Friese group, you have to show that there is a unique translation that generates all the translations in that group. Okay, so just showing you another form of how to present F2. By the way, that's I think, remember, that's what we call when you show a group's generators and the relations between those generators. That's called a presentation. Okay, I think we've said that before, but if not, a good piece of terminology for those of you going on to group theory. Okay. So let's draw a pattern that has F2 as its group of symmetries. The following has F2 as its symmetry group. Okay, same type of setup, right? I have solid dots and hollow dots for A's and M's respectively. How many did I draw here? 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. 7, 8, 9. Okay. So how does this one go? We have this, 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 here, here, and here. Okay. So it might appear as though we haven't done much yet, but let me point something out. Notice that any Friese group containing only even isometries must be either F1 or F2. Okay. So let me just say the remaining five possibilities are based on adding in odd isometries as generators to F1 or F2. Okay, this is how we'll proceed. Okay, so first, let's consider the possibility what happens when we allow reflections. What happens when we allow reflections as generators? So just some basic facts about reflections that we should remember. So recall that reflection L, I'm sorry, sigma sub L, a reflection in L, fixes center C, the center of the Fries group, C, if and only if either one of two possibilities. C is equal to L or C is perpendicular to L. Right? That's from our study of the basic properties of reflections, right? Reflections fix their line of symmetry pointwise, and they fix every line perpendicular to the line of symmetry. Okay. So okay, so on to possibility 3. Let's set F11, one in the superscript and a subscript 1, to be the group generated by Tyler translation and reflection in C, the center of our Fries group. Now, since tau, the translation, fixes C, what do we know? Well, remember, we kind of did a case-by-case study of when isometries commute. And one of those cases is when you have a reflection in a line C and a translation which also fixes that line, then those isometries commute, right? So that is to say, in symbols, tau sigma C is equal to sigma C tau. Okay, we proved that in class a couple weeks ago. Okay, so what does this tell us? Well, this tells us that our Fries group F11 is abelian. That is, it's a commutative group. Okay. And furthermore, all elements are of form sigma sub C to the J, tau to the I, for some I and J. Okay. Well, here's some other observations about F11. F11 must contain the Glide reflection with axis C, which takes, taking A to A sub N. That is to say, this is the equation of a glide reflection, right? We have a translation followed by a reflection. Okay. Right. So, in other words, this would just be, namely, sigma C tau to the n, right? Tau to the n takes A to an, and this is a glide reflection, which does that. Of course, since A and an are on line C, they're fixed by sigma C. Okay. So now, okay, this is our first. Here's what I want to say. This is our first appearance of a glide reflection in a Fries group. However, note that I haven't written it as a generator. We'll come back to that point once we finish our classification. Okay, I just want you to be aware of that. Just note that now. Okay. So a pattern with the symmetry group is the following. Same notational convention. Solid dots are A's, hollow dots are M's. Nine. simple pattern that has F11 as its center. Okay. So now what I want to do is throw in a want to throw in a reflection into F2 is what I'm going to do. Okay. But first, I'm just going to get a drink of water. I'll be right back. Okay, sorry about that. Right, so now we're going to add in a reflection to F2. So we move on to possibility 4. And we're just going to set F21 to be equal to the group generated by tau, the half turn at A, and the reflection in line C. Okay. So, firstly, note that sigma C commutes with both sigma sub A and tau. Why is that? Who can remind me why sigma C? Well, let's start from the beginning. Why does sigma C commute with sigma A? Yeah, exactly. A is on C. Right, good. And why does sigma C commute with tau? We just said that in the last possibility, right? Because tau fixes line C and so does reflection in C. So therefore they commute. So therefore every element of F21 is of the form sigma C to the K, sigma A to the J, tau to the I, or sum I, J, and K. Okay. So now here we're going to see, not surprisingly, we'll see that this Fries group contains glide reflections as well. Right? So specifically, For n not equal to 0, what do we have? We have that F21 contains the glide reflection sigma c tau n with, of course, axis C, and taking A to N. And this is just like the case with F11, but also F21 contains tau to the 2i times sigma A, sigma C, which is reflection in the line perpendicular to C, at A sub I. Okay. And furthermore, F21 also contains tau to the 2i plus 1 sigma A, sigma C, which is reflection in the line perpendicular to C at MI. Okay. Therefore, if we set the line A to the perpendicular to C at point A, right? We can write F21 as follows. F21 is generated by tau sigma A, that is sigma little a, sigma C. Okay. So, in other words, even though we started by augmenting F2, in fact, we can write F2 so that it has generators, so that all the odd generators, so that tau is the only even generator. That's what I mean to say. Okay. there you have it. Let me draw you a pattern that has this symmetry group F21. Okay, and same schematic. Okay, so like this. There you have it. Okay. Right, so that is to say, I can reflect through any perpendicular to the line C, right? My through line is C here, and say here's my A, right? Then obviously I have reflectional symmetry about the line that comes through, right? And of course, I just shift this by tau, right? Okay. So what can we say if we assume that F does not contain a half-term, but it necessarily contains a line, reflection in a line perpendicular to C? Well, let's discuss that in some more detail. What I mean. Okay. So now let's suppose some Frieze group F does not contain a half-term, but does contain a reflection in a line perpendicular to C. Okay. Then remember, going back to our choice of A, right? The point A, then we suppose A lies on the line A, which is perpendicular to C. Okay. So this implies, well, since we started with the assumption that F is a Fries group, we know that it has some translation in it, right? So in particular, we know that tau to the 2i sigma sub A, the line A, this is reflection in the line perpendicular to C, passing through A sub I. Okay. And similarly, tau to the 2i plus 1 sigma A is reflection in the line perpendicular to C, passing through MI. Okay. So with those observations in hand, we can now discuss possibility number 5. Okay, so let's assume that F contains another reflection. Sigma sub L. Okay. So then we know that L cannot equal the center C. Why is that? This is a little bit tricky. Think about this for a second. Why can I deduce that assuming that F, okay, my F here, these are all my assumptions on F. Assuming that F contains some other reflection, sigma sub L, how do I know that L cannot equal C? Any thoughts on that? No? Okay, well, so since if L did equal C, if L were C, then sigma C, sigma A would be an F. Now, why is this a problem? What's the relationship between A and C, lines A and C? Yeah, thank you, Spencer. This is a half turn, right? Because A and C are perpendicular. So the product of their reflections in A and C results in a half turn centered at A. But we assumed that F did not contain any half turns. Therefore, this reflection line L cannot equal C. Okay, good. This implies since L is perpendicular to C, we know that sigma L, sigma A equals tau to the n or sum n, right? That is to say, L is perpendicular to C and A is perpendicular to C. Therefore, L and A are parallel. And two reflections in two parallel lines results in a translation. So it's some power of tau, this translation that we're given by the fact that F is a Freeze group. Okay. So what does this tell us? Of course, for some n, and then we also know, naturally, taking A to an. Okay, so that is to say, we'll make a similar computation to one that we've made several times before. Sigma L, sigma A of A is just sigma L A, right? Since sigma A fixes A is on the line A, equal to AN. So, in conclusion, L is perpendicular to C at AI or MI for some I. Okay, so putting this all together, yeah. then what we'll do is we'll set, and we set F12 equal to the group generated by tau and a reflection in line A, where A is perpendicular to C at point A. Okay, so in other words, we added in a reflection to F1, right? Okay, so again, we have this relation. In F12, we have the relation tau sigma A is equal to sigma A tau inverse. Okay, so think about this. So every element of F12 is of form sigma A to the J, tau to the I for some I and J. Okay, so let's see a schematic that has this symmetry group. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so this, 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 this. Okay. Note the absence of reflection in C. We don't have that here in F12. Okay. But other than that, go back and compare this to the pattern that has symmetry group F21. It's just the same, except we don't have the bottom half, right? There's no reflection in C. Okay. So now, before we move on, let me just ask you, what do you think the next step is? What will we do next to see what's possible for a freeze group? Or perhaps in a more leading way, what types of isometries have we not addressed the possibility of adding in F1 or F2? Oh, I'm sorry. So, is this better? Am I, okay. So, my question was, what types of isometries have we not dealt with yet that we could add into F1 or F2? anybody else having the same problem as Keenan? Any a bit at some point? Okay. Um, all right. I'll try to speak louder and be closer to the microphone when I'm speaking. Like, so does this sound okay? Can you is it cutting in and out here? Or am I
First
generally
better, I think. Like where you just were was good.
okay?
Yeah.
Okay. So, all right. My question was, what are the isometries that we haven't addressed yet? What types of isometries have we not yet attempted to add in as generators to F1 and F2? Well, we covered everything even, right? That was our first investigation, and then we moved on to odd things, and we've just dealt with reflections so far. So Zach's got it. We've got to talk about how we can possibly add glide reflections in as generators. Okay. So, and these are the remaining two cases. We won't have time to actually fully complete the sixth possibility, but let's start. Okay. Okay. So let's start by supposing now, assume F contains a half turn and a reflection in some line Q. Okay, no assumption here about Q's relationship to C, but we've actually covered a fair number of cases that we'll enumerate now. Okay, so we'll assume that F contains some reflection in line Q. Okay, so if Q equals C, or Q is perpendicular to C at AI or MI for some I, well, then we're just back to F2 comma, I'm sorry, F21. Then we're in the case of F21. Okay, so do something new. I guess I should say to generate new possibilities. We must assume that Q is off AI and MI for all I. Okay. So, then what we do is assume that A is the center of a half turn that's contained in F. Okay? Okay. So, assuming A is the center of a half turn, in F, sigma Q of A must be the center of some other half turn in F. Okay. So why is this? It's the main theorem. It's the main theorem that we have used today about conjugation, right? That is to say, so we're assuming sigma Q is in F, and we have this half turn that has center A. So when we conjugate by that is to say, when we conjugate the half turn by this reflection, what do we get? We get sigma sub sigma Q of A, which is, of course, in F, just because of the axioms of a group. Okay? So, what does this tell us? This implies that Q must be the perpendicular bisector of A of the line segment AMI for some I. Okay. So, all right. So, I think this is a good stopping point. So it might be still a little unclear how glide reflections will appear, but the computation is slightly involved, and I don't want to get halfway through it and then have to redo everything tomorrow to remind you. Okay, so I will see you all tomorrow, and I think after class tomorrow, I'll send out the solutions to the practice exams. Okay. All right, everybody have a good day.